Back, Chapter 2, Section 2.2, the derivative as a function. We have considered the derivative of a function f at a fixed number a using this particular definition. F prime a is limit h approaching 0 or the fraction fa plus h minus fa the whole over h. Now, here we want to change our point of view and let the number a vary. Vary meaning we want a to be able to change. If we replace a in this equation by x, we get this definition of the derivative function. F prime x is limit h approaching 0, f of x plus h minus fx the whole over h. Okay, all we have done is replace a by x. Given any number x for which this limit exists, we assign to x the number f prime x. That is, f prime is a new function. This is what is called the derivative function of f. We know that the value of f prime at x can be interpreted geometrically as the slope of the tangent line. The function f prime is called the derivative of f because it has been derived from f by the limiting operation. The domain of f prime is the set of all those x's where f prime exists. So notice, domain of f prime need not be the same as domain of f. In fact, it may be smaller than the domain of f, because not only do you want fx to exist, you want f prime x to exist. Okay, here is graph of a function f. You can use the graph of fx to graph f prime x. So what do we do? Well, that is f. You are estimating the value of derivative, okay, by using some tangent point and estimating its slope and so on and so forth. So if you like, let's get close to it here. So you see, here is a number where derivative has to be 0. It has to be 0 because tangent line is horizontal. Okay, so at that number, your graph, here's the x-axis. The derivative graph hits x-axis because that's what it means to have 0 value, right? So derivative has value 0 here. Why is this negative here? Look to the left. My graph, my slopes are all negative. All the slopes are negative, and therefore my derivative is all below x-axis. Between, what is this b prime? Look at that. Another place where derivative is 0 because the slope is 0. So these are my x-intercepts. Why is it above the x-axis here? Well, look here. I'm increasing. All the slopes are positive. All the slopes are positive. So the derivative has to be positive. But it has to come back to 0 height, and therefore it has to take a term. Likewise, the next time derivative is 0 is over here. So this is how you go, step by step by step. All right. Okay. So this is the same discussion that we went over. Now, notice when you have horizontal tangents, derivative is 0. And so the derivative has to cross the x-axis. All right. When you have positive slope, derivative is positive. When you have negative slope, derivative is negative, because that's what derivative means. Derivative means slope of the tangent lines. Okay. Now let's consider square root x function. When x is close to 0, square root x is also close to 0. But if you have gone over, I think, Did we see this? No. Okay. If you go over and calculate the derivative of this using definition, limit h approaching 0 and so on, you will get derivative to be this. Look at the graph of f and look at the graph of f prime. When you are close to 0 here, you are approaching 0, no problem. But look at the slopes. All these slopes are positive, but the slopes are very high here, steeper and steeper, and that's what is it. All our derivatives are positive, but as you get close to 0, you are very high value. Okay. When x is large, f prime is very small, and this corresponds to the flatter tangent lines. Whereas if you go far away, you see this is getting flatter. It is not growing fast. You see, it is getting flatter. That is, the slope is getting closer to 0. That's all they are saying. All right. So I hope you have a geometric understanding of what derivative means. Other notations, if we use the traditional notation y equals fx to indicate that the independent variable is x and the dependent variable is y, then some common alternative notations exist. Okay. F prime is the notation we have used so far. Another way of, so this is called, by the way, Newton's notation. Here is Leibniz notation to mean the same thing. F prime, instead of writing all F prime, you would write dy dx or df dx. Mind you, you don't cancel d's. They just mean the phrase derivative of y with respect to x. Derivative of f with respect to x. That's what this means. Another notation, d by dx, fx written completely, or capital D of fx, or capital D with a sub x fx. Okay, so capital D and d by dx are called differentiation operators because they indicate the operation of differentiation. All right. So to remind you, f prime is the notation introduced by Newton. This is notation by Leibniz, and they mean the same thing. Do not make the mistake of cancelling d and d. That makes no sense. This essentially is a short form of saying the entire sentence, derivative of y with respect to x, or derivative of f with respect to x, so on. The symbol dy dx, which was introduced by Leibniz, should not be regarded as a ratio. It is simply a synonym for fx. Synonym means it means the same thing as f prime x. Nonetheless, it is a very useful and suggestive notation. Why is it useful here? You may think of dy dx as limit delta x goes to 0, delta y, delta x. So maybe you can see something. Basically, dy dx actually has advantage when you go to a function with many variables. All right. Other notations, continuing. If we want to indicate the value of a derivative dy dx in Leibniz notation at a number a, you could write dy dx, a long line, x equals a in the bottom, or dy dx, closed bracket, x equals a in the bottom. They both mean f prime a. Okay. A function f is said to be differentiable at a number a if the derivative of f at a exists. It is differentiable on an open interval a to b, or a to infinity, or negative infinity to a, or negative infinity to infinity, if it is differentiable at every number in the interval. So what does differentiable mean? Derivative exists. When do you say derivative exists? When that limit exists. Okay. Now that exists at a number a, you say f prime a exists. If that limit exists for every number in your interval, okay, then you say your derivative exists on that particular interval. Okay, so the next slide I will start on the next video. Will work on the main example now. Until then.